All right, so let's begin. Um, okay, let's begin. You can see the first question. So we know that the summation of a function, when we do that summation at very small discrete steps, you can almost equate it to an integral. This you already know, kind of you already know since your 12th grade. We've seen this kind of an expression in the 12th grade as well. Um, but here the expression that we want to evaluate is going to be a little bit trickier. So let's do it though, nonetheless. So this question, at least the one part of this question, I'm going to show you fully because it is a little bit trickier. So I myself had to go through uh, books and internet both to actually get to the solution of this. So this question I will show you fully, uh, and that only one part of it. The second part is quite easy. You can do it yourself. Okay, so let's go ahead. All right. So here we begin with assignment 2. Okay, so the first question is that the summation, we know it can be equated to an integral. Two the specific functions have been given. F of x is equal to 1 divided by x square plus a square, and another function is f of x is equal to e raised to the power of minus mod x upon a. Um, and there is third function as well. F is between minus a to a. Between minus a to a, f of x is 1, and otherwise f of x is equal to 0. So you want to carry out the summation also of these functions, and you want to perform the integrations also, and you want to see whether the results match or not. That's the motive of the question. The second and the third part, see, the integrations part are completely straightforward. For the first part, the integral everyone knows is going to be tan inverse x by a. X square plus a square is tan inverse. So the first part is pretty straightforward. You do the integration, set up the limits, and the right hand side is very clear. So the left hand side is the summation, the right hand side is the integral. The right hand side integral is very clear how to do it for all three. For f of x is equal to minus e raised to power minus mod x upon a, even then the integration is quite straightforward. For the third part also integration is straightforward. The only thing that may go complicated is the summations. So for the first question, for the first equation, which is this one, f of x is equal to 1 upon x square plus a square, the summation wasn't exactly straightforward. Uh, at least I couldn't find any trick which was easy. If you do know something, please do tell me. But according to me, this summation is quite a difficult one. So this I will show you. The second and the third summations are also relatively straightforward. So actually you can go ahead and do them yourselves. The first one I will show you. Okay. So let's go. Um, First one is f of x is equal to 1 upon x square plus a square. So when I'm writing it as f of lambda n, it will be 1 upon lambda square n square plus a square, sum over n equals 1 to infinity lambda 1 divided by lambda square n square plus a square. This is the summation that we want to evaluate. Okay. Now, basically what's happening here is lambda, right? The limit lambda tends to 0. Of course, in limit lambda tending to 0, this is what we want to evaluate. Okay. That's my LHS. Let me evaluate the RHS first. RHS is directly the integral, right? So RHS is integral dx 1 divided by x square plus a square. This goes from minus infinity to infinity, and I have to do a half is equal to half integral. The integral basically gives you tan inverse x by a is equal to half of uh, minus infinity to infinity. Sorry, 1 by a tan inverse x by a. Right, the integral is 1 by a tan inverse x by a. So there is a half here, 1 by 2a outside, and infinity will give me pi by 2 minus pi by 2. So the answer is pi upon 2a. That's my RHS. What I want to do is actually see that the LHS also gives me the same value, and that's when I can prove or I verify that the summation that is shown on the left hand side is same as the integral on the right hand side, the integral that we have already performed. So let's carry out the summation now. For this summation, we require some tricks and some complex integration. So basically, pi okay, so suppose assume that there is a function of this form. Let me verify whether I'm doing it correctly or not. Pi cos pi z on sin pi z. Yes, yes. So this is my function. Right. So okay. So what I want to do is I want to evaluate the limit of this function. Evaluate. I'll tell you the motivation why I'm doing this, but let's do this first. Evaluate the limit of this function at the poles. And what are the poles of this function? The poles of this function are at z equal to n, right? Because in that case, the denominator becomes sine n pi, and the function shoots up. So that is why this is a pole. So I want to evaluate the limit of this function at all the poles. Basically, at all the integral values of z. At all the integral values of z, I want to evaluate the limit of this function. Again, I will tell you the motivation. First, let's follow the steps that I am saying right now. Okay. So limit z tends to some n. Um, Actually, right. Sorry, my bad. What I want to do is evaluate this limit. This is the function that we are considering. This is some additional random function that we are considering. What I want to evaluate is this limit. Limit z tends to n pi cos pi z upon sin pi z into z minus n. Okay, so in the limit z tends to n, what happens is pi cos pi n divided by sine pi n into some delta z minus n, some delta which is a very small number. Right, so limit z tends to n, because it's just a limit, so I'll say it's some n plus delta maybe. I'll not put it as exactly that, right? So cos pi n minus cos pi delta cos a plus b is cos a cos b minus sin a sin b divided by sin of sin a plus b. So that is sin a cos b sin pi n cos delta plus cos a sin b cos pi n sin delta multiplied by delta pi into this. So limit z tends to n pi cos pi n cos delta. Cos of pi n gives me uh, cos pi is minus 1, cos 2 pi is 1. So cos n pi can be minus 1 raised to the power of the integer, minus 1 raised to n, minus 0, because sin pi n is going to give me 0, divided by sin pi n cos delta is a 0 plus cos pi n again gives me minus 1 raised to the power of n, and sin delta will stay as it is, sin delta multiplied by delta, right? So this minus 1 raised to power n minus 1 raised to power n exactly becomes 1. So what I get is limit z tends to n of this function is exactly pi. Okay, I hope I'm not missing something here. Um, Actually, this is pi delta. My bad. See, I made a mistake here. This is pi delta. So this limit z tends to n is exactly 1 of this function. Okay, so let me tell you again what is the first step to solving this problem. I assumed some random function pi cos pi z upon sin pi z. Okay, this is some random function that you don't know about. This is some random function that you don't know about. What I said is I want to first evaluate the limit of this function multiplied by z minus n. Why I am doing this is because eventually I will be using this function and calculating the residue. And while calculating the residue, this sort of expression will appear. So I want to first get away by evaluating this limit itself. So that's why the limit of this function at z tends to n multiplied by z minus n. There is also the z minus n factor. So this limit will be useful in evaluating the residue of this function. So I come to know that this limit when z tends to some integer value is always 1. Okay, so I'll again rewrite what I evaluated till now. Limit of z tends to n pi cos pi z divided by sin pi z multiplied by z minus n. The limit of this function when z tends to n is equal to 1. This is the only thing I evaluated. You might still not see the relation of this thing with the problem, but you will come to know eventually. Okay, so now next what we will do is, what are the poles of this function? Pi cos pi z divided by sine pi z. What are the poles of this function? Poles question mark. The poles of this function are basically z belonging to all the integer values. When z belongs to any integer value, those are the poles of the function. So z belonging to basically all minus infinity to infinity, all the integers are its poles. Okay, so now let's do this. So what I'll do is I'll write some integral of this form, some contour integral of this form, some f of z multiplied by pi cos pi z upon sine pi z dz. Suppose I have an integral of this form where f of z is some function and it is multiplied by this pi cos pi z upon sine pi z. I multiply these two functions. I and I want to evaluate the contour integral of this. Okay, so what happens is in this case the answer to this contour integral, where this contour goes from in the complex plane, this contour is this entire minus infinity to infinity. It's a contour at infinity. Okay, so if this is the contour over which I'm integrating, and this is the function whose contour integral I want to evaluate, so in that case what is the answer? The answer is residue at z equal to exactly how do I write this? Basically what will happen is uh, sum over z is equal to poles of this function, poles of pi cos pi z upon sine pi z, residue of pi cos pi z upon sine pi z multiplied by f of z is equal to poles of this poles of pi cos pi z plus z equal to poles of f of z, residue of f of z multiplied by pi cos pi z upon sine pi z. So we are basically using the residue theorem that if you want to evaluate the contour integral, we'll what we'll do is at all the poles of this entire function. So where are the poles of this entire function? The poles of this entire function will be at wherever there are poles of f of z. If f of z has some poles, so we have to evaluate the residue at the poles of f of z multiplied by pi cos pi z upon sine pi z. The z will be the value of the pole of f of z. And we also have to evaluate at each and every pole of the second function pi cos pi z upon sine pi z. We have to evaluate this, we have to evaluate residues at poles of both the functions. Okay, so if you understand this much, and okay, one more point I'll add and then I'll ask. Uh, the poles of this function are just all the integers, and the residue of this function at those poles is just 1. This residue is 1. So what I get is basically The right hand side, one of the terms is sum over all integers, sum over all the integers f of z plus the residue of f of z term multiplied by pi cos pi z upon sin pi z. This is the right hand side, and the left hand side is basically the integral is at infinity. So because of the nature, we are assuming that the nature of the function is going to be of a certain kind. So this integral is always going to give us 0, because the function that we are going to use has to be a decaying function of that form. F of z has to be that kind of a function. So because f of z is actually 1 upon x square plus a square, we are using functions only of that sort. So at infinity, the integral actually will always give you 0. So the left hand side is 0, but the right hand side will have two terms. One of the terms is the summation that we want, and the second term is just this, which is very simple to evaluate. So simply by evaluating the residue of f of z in the complex plane, multiplying by this new function that we assumed out of nowhere, we can evaluate the summation of this function. I know this was a little bit complicated. If you have any doubt, please ask me right now. Any particular point I can explain again. If I have not been able to make you understand properly, I will help you a little more. I will make you understand a little bit better. So please tell me if you have any doubts here till now. If anyone has a doubt, please ask away right now. If you are feeling that you have no understanding of what is going on, if you have been listening properly, but you are not able to follow the method that I'm trying to use, you can feel free to ask me that you do not understand the method. I can explain it to you again. Did everyone understand the method that we're trying to use here? Okay, nonetheless, I'll just quickly, briefly tell you again. So what we are doing is we want to evaluate this summation. The original purpose was we want to evaluate this summation right here. Lambda multiplied by sum over n equals to 1 to infinity 1 divided by lambda square n square plus a square. This is the summation that we want to evaluate. To evaluate this summation, I understand that normal techniques won't suffice. What I'm trying to do is I'm trying to evaluate this summation by going into the complex plane. Now, by going into the complex plane, how do you do that? Generally, we try to use residue theorem in some form of or the other to evaluate these kinds of summations. You might have learned in complex analysis that to evaluate complicated summations, we tend to use residue theorem. We tend to assume some kind of function. So what I did was I assumed a particular kind of function whose poles are exactly at z equals to integer value. So this is that function that I assumed, and the pole that this has at every integer is just the first order pole. Because it has a first order pole, I can simply evaluate the limit at z tends to n, and you know that the limit is 1. We saw that evaluation of the limit. So now to evaluate the summation, what I'll do is I will multiply this complicated function pi cos pi z upon sin pi z with my function f of z. I will multiply these both, and I will try to evaluate the contour integral. By doing so, when I use the residue theorem to evaluate this contour integral, what I see is that I have to evaluate the residues at poles of all the functions of the entire function. And there are two kinds of poles. One is the poles of just this function pi cos pi z upon sin pi z. That is one part. And those poles are basically z equal to integer. And the other poles come from f of z itself. So that is why I split this evaluation into two parts. One part has poles of pi cos pi z upon sin pi z, and the other part has poles of f of z. So poles of pi cos pi z upon sin pi z are integers, and the residue of it is just 1. So basically, using residue theorem on poles of just pi cos pi z function will give me the summation that I want. When I use the residue theorem only on poles of this function pi cos pi z upon sin pi z, I get the summation that I want, which is this summation f of z. From the poles of f of z, I will get some term which I have to evaluate, and the left hand side, which is actually the contour integral, is actually 0, because think of it, 1 upon z square plus a square. This is the function that we are talking about. At infinity, z actually tends to infinity. So z actually tends to 0, 1 by z square plus a square tends to 0. So actual contour integral of this is going to be 0. So the left hand side is going to be 0. The right hand side has two terms. So which means that the summation equals to the negative of this term. So I simply evaluate this term. And I get the summation value. Okay. So now let's go ahead and evaluate this. So what is my f of z first? F of z is this 1 upon lambda square n square plus a square. 1 upon lambda square n square plus a square. Or I can also write 1 by lambda square into 1 upon n square plus a square by lambda square. Alright, so my n is basically separate from lambda. So what are the poles of this function? Uh, the poles are simply n plus I a by lambda, comma n minus I a by lambda. These are the two poles of this function. Okay, so residue of the other function. Actually, residue is going to be of the entire thing, not just one particular function. What is the residue of this entire function for these two poles? So residue at z equal to n plus I a by lambda of 1 upon n square plus a square by lambda square multiplied by pi plus residue z equal to n minus I a lambda 1 upon n square plus a square by lambda square divided by pi cos pi z sin pi z. So here to evaluate the residue, obviously what we'll do is I'll uh, here actually n is z. My bad, sorry. So the function f of z is equal to 1 upon lambda square z square plus a square. That's my function. 1 upon lambda square z square plus a square. This is my function. So I take out lambda square z square plus a square by lambda square. Right. So what are my poles again? My poles are z equals to uh, plus minus I a by lambda. Z equal to plus minus IA by lambda are my poles. So residue at Z equal to minus IA by lambda, uh, Z square plus A square by lambda square multiplied with this Z square plus A square by lambda square, Z equal to IA by lambda. These are the two poles at which I have to evaluate the residue. So let's go ahead and do this. Um, so the first one is I will remove Z plus IA by lambda. That will go away. So 1 upon Z minus IA by lambda is going to stay because I'm evaluating the residue. So that's a very standard thing to do, right? And I'll substitute minus A by Z as minus IA by lambda. So then this becomes minus 2IA by lambda multiplied by pi, which I'm taking here, cos pi Z minus IA by lambda sin pi minus IA by lambda. Pi lambda divided by minus 2IA. Cos pi minus IA by lambda, I'll simply write cos as e raised to power. So cos x is e raised to power ix plus e raised to power minus ix by 2. So I'll write cos e raised to power I pi minus pi I a by lambda plus e raised to power minus I minus pi I a by lambda divided by 2 divided by sin x is e power ix minus e power minus x ix by 2i. So I minus pi I a by lambda minus e raised to power minus I pi I by lambda divided by 2i. So 2i I will remove from here. It will get eliminated. Is equal to minus pi lambda by a e raised to power pi I becomes minus 1 plus pi a by lambda plus e raised to power minus pi a by lambda. I becomes minus pi. This is my first residue with negative sign. Okay. What's the second residue? Along similar lines, I will be getting second residue as pi divided by 2ia by lambda. I am evaluating this term now. Pi divided by 2ia by lambda multiplied by pi. Sorry, there is no pi now. I've already taken pi. Cos of pi z, where z is equal to ia by lambda. Ia by lambda by sin pi ia by lambda. Same thing again that we did previously, e raised to power I pi ia, which is minus pi a by lambda plus e raised to power pi a by lambda divided by e raised to power minus pi a by lambda minus e raised to power pi a by lambda. The 2I will go away from here. Again, just like previous step. Therefore, pi lambda by a, because lambda is tending to 0. Um, what am I missing here? I'm missing something, I think. Okay, right. Sorry. So what I eventually got here, because lambda is small, so 1 by lambda is going to be large. So any term of this form is going to become 0, 0. So this is what? Simply minus pi lambda by a into 1. What about this term? Again, here also, this is going to be 0, this is going to be 0, and it's going to be minus 1. So even this is the same. So what I get is, this gives me um, both the terms are practical this. They are exactly the same. So that's why I get minus pi lambda by a minus pi lambda by a minus 2 pi lambda by a. Oh, my bad. There is a 2 which stays here, which I actually removed. The 2 here actually stays. If I'm seeing the calculation properly, there will be a 2 here. Only the I will go away, yes. So this is actually minus pi lambda by 2a. So this is just pi lambda by a. Right. And there's this is just this. And I also had taken out 1 by lambda square common. So I just evaluated the summation of this inside, right? So my entire expression was this, that lambda divided by lambda square which I had taken out, sum over z belonging to integer, this thing. So it is basically 1 by lambda minus pi lambda by a. So that's why it's just minus pi by a now. So the summation yields that. Evaluation of this term yields that, sorry. This residue yields that. So basically what it's trying to say is sum over f of z over z belonging to is equal to positive pi by a, because it will go on the other side. So it yields me simply positive pi by a. What it said was summation gives me half of this. Somewhere I might have missed a factor of half. So you can actually check that. But I have missed somewhere a factor of half. So I'll have to check that properly. This is a little bit complicated calculation. But the whole point of doing this like this is to show you exactly how this kind of problem is done. So to summarize, we multiplied it with a function which has poles at all the integer values. So the function that we have, which is 1 upon n square plus lambda square, a square by lambda square, 1 upon n square plus a square by lambda square. This is my function. I multiply it with a function which has poles at all the integer values. I take a contour integral of the combined function over the entire complex plane. My contour is the entire complex plane, like the edges of the entire complex plane. That's my contour. If I evaluate this kind of a contour integral, it by default yields a summation term and another term wherein I have to evaluate the residue at only the poles of f of z. So basically it all boils down that the summation evaluation boils down to evaluating residues of the function, combined function, only at poles of f of z. So by evaluating the residue at the poles of f of z, I get the answer to the entire summation. That is the method that I have followed. If at all you have any doubts or questions here, you can go ahead and ask, or else we can move on to the next question. I have missed a factor of half somewhere, and it's anyway taken quite a long time. So I don't want to go back and check where my factor of 2 has missed out. So if you know the method, you can just go ahead and evaluate. This is a proper foolproof method. I think I had taken this from RFCAN itself. I was referring multiple sources, but RFCAN also had something similar to this. So you can go ahead and check out other kinds of summations which can be evaluated by complex integrals. It's a very interesting way of evaluating summations. Like you might not ever think that summations can be evaluated by complex integrals, but it's a very interesting method. So you can do that. So this is the end of first question that I am going to show. The LHS evaluation is the only thing that I've shown in this. The RHS evaluation is straightforward. You know that. RH and LHS evaluations for the second and the third part are also very straightforward. So even that I'm not going to show. So that is going to be your job. If you have doubts, you can ask on the forum and uh, other places, but they are pretty much straightforward. So if at all you have some doubts, the second one is just simply for x greater than 0, it's simply e raised to power minus uh, n lambda by a, sum over n, right? Well, and lambda is outside. So this is simply a geometric progression. It's simply an infinite geometric progression. So the summation for the second part is simply the sum rule or the sum formula of a simple geometric progression which goes to infinity. So that you can do. The integral is very straightforward. You know how to evaluate the integral. Even that I'm not going to show. And you can do other things, the other part also. That is just a simple stepwise defined function. So that also you can very easily do. So that ends question number 1. Let's move on to question number 2. Okay. In general, they are saying that in general the entropy. I know I have not put down one option here. One or two options are missing. But let's read the question and evaluate uh, ourselves, and then we'll see what the options are. In general, the entropy of any gas may be written as in general entropy of any gas may be written as S of u v n is equal to n into S of u by n v by n and 1. Show that this entropy function is extensive. Imagine that for a certain gas, the entropy function is of this form. Find the equation of state of this gas, that is, find the ratio R is equal to PV upon NT in terms of V by N, and temperature T. What is the chemical potential of this gas in terms of temperature? And V is equal to capital V by N. What is the energy per particle? What is the value of R for a classical ideal gas? Okay, so there are many parts to evaluate. Firstly, show that this entropy function is extensive. How do you show that? This is the first part that I'm evaluating. S of U V N, they're saying, is just simply N S of U by N V by N 1. So to see that if it's to see whether the function is extensive or not, U I convert to NU, V to NV, and N stays the same. Actually, we'll simply U will go to some K into U, V will go to some K into V, and N will go to some K into N. Okay, so in that case, extensivity tells me that F of KU, KV, KN should be equal to K into F of UVN. That is the definition of extensivity. So let's see whether that applies to the above entropy equation. So S of KU, KV, KN is equal to KN S of KU by KN. kv by kn 1. K gets cancelled. N into S of u by n v by n 1 is just S of u v n. So therefore S ku kv kn is equal to k into S of u v n. It actually satisfies this condition. That's why this is extensive. This entropy function is extensive. Okay. Now they are saying imagine that for a certain gas S of uv1 is u cube v square. S of uv1. Note that all these letters are small alphabets. They are not capital. So here when we are saying uv1, we are saying u is basically internal energy per particle. V is volume per particle is equal to u cube v square. So practically this is also entropy per particle. Now from here I want to actually evaluate the total entropy. So I have to simply multiply by the number of particles n. S of u v n is simply n into S of u by n v by n 1, right? And this is basically u cube v square. So therefore the proper full entropy function is S u v n is equal to capital N multiplied by u cube v square, which is equal to n into capital U cube upon capital N cube, capital V square upon capital N square. So S of u v n is equal to u cube v square divided by n raised to the power 4. Okay, now what they are asking is find the equation of state of this gas. Actually, it's awfully silent today. Can someone say if I'm audible or not, at least? None of you guys are asking any question. I don't see any kind of response. So I am audible, right? And you guys follow what I'm doing. Please, someone say something. Uh, I think Rashi was it, right? Rashi, please speak up again. I couldn't hear you. I'm audible, right? And uh, are you guys able to follow what I'm doing till now? Please feel free to ask doubts if there are any. It might get like I might not be able to explain some things perfectly. So if you have doubt, stop me right there that you were not able to follow that. I'll explain it again. Okay. So having said that, this is the entropy function that we have, and what we want to do is using this we want to find the equation of state of the gas. So firstly, um, how do you find all the expressions that we want? Firstly, U is equal to T is equal to del U by del S, which is 1 by T is equal to del S by del U. Therefore, 1 by T is equal to, I'll differentiate with respect to u. So that gives me u square v square by n raised to power 4 is 1 by t. Actually, s is equal to du by t plus v dp plus n d mu. Um, Del s by del v is equal to p, p dv. I'm actually not very sure about this expression, to be honest. Del s by del v is equal to p by t, and this is equal to I mean, okay, so 2 u square v divided by n raised to power 4 is equal to p by t. There's a 3 here. I'm doing some wrong math. So 1 by t is 3 u square v square divided by n raised to power 4. Del s by del v gives me 2 u cube v upon n raised to power 4. So using this to eliminate u. How do I eliminate u here? Uh, n raised to power 4 divided by 3 t v square. 3t v square is equal to u square. Therefore, u cube is equal to n raised to power 6 divided by 3t raised to power 3 by 2 and v cube. Therefore, p by t is equal to 2 n raised to power 6 v divided by 3t raised to power 3 by 2 v cube and n raised to power 4. So this becomes 2, this becomes 2. So 2 n square divided by v 3t or 3 by 2 is equal to p by t. What kind of expression is expected? PV by NT. We want PV upon NT. So PV divided by NT is equal to 2N. This is V square, right? Okay, so there's not just V. So V square remaining. How are the options looking? T raised to power 3 t raised to power minus 3 by 2. That we already have. So this is 3t raised to power minus 3 by 2. What I have is 2 by small v. Okay, let's evaluate the other quantities first, and we'll get back to this a little bit later. So what is the chemical potential of this gas in terms of temperature and V is equal to V by N? So having evaluated this, we can also evaluate temperature. We have evaluated PV by NT. We got some expression which is not exactly matching with the ones given. Next step is evaluate chemical potential. So for chemical potential, it is simply del S by del N minus 4 U cube minus 4 U cube V square upon N raised to power 5. This is my mu. Mm, if I minus mu by t, this is minus mu by t, del s by del n, right? So minus 4 v square upon n raised to power 5 minus minus actually gets cancelled into t into u cube. The expression for u cube n power 6 3t raised to the power 3 by 2 v cube. This is the entire thing. This goes away, this goes away, this goes away, is equal to 4t n 3 raised to power 3 by 2. So 4 divided by small v 3 raised to power 3 by 2 t raised to power 1 by 2. V into 3 raised to power 3 by 2 t raised to power 1 by 2. So here if you see the options, 4 into 3 raised to power 4 divided by 3 raised to power 3 by 2 t raised to power 1 by 2, and there is 1 by v also. Yes, so we can see that this option matches. The mu part is matching with only one answer, but I for some reason suspect that this is what we evaluated is not incorrect. That is correct itself. And that is the answer 2 by v rather than 5 by v minus 3, because this does not even make sense unit wise. Here the units are 5 by v has some unit and 3 is just a number, it has no unit. So I believe there is some mistake here. But anyway, we evaluated R, we evaluated mu. For classical gas, R is equal to 1. R is PV by NT. For classical gas, PV by NT is what? For a classical gas, PV by NT is actually equal to 1. R is equal to 1. Uh, what is the value of small u? Small u we already evaluated. We just evaluated u square, right? So u is equal to n square upon 3t raised to power half v square. So u by n is the small u, so it's just n divided by this. So yes, that is the answer that we get is equal to 3t raised to power minus half divided by small v. So that's why it seems that this is the correct option, because we match except R Well, answer except the answer which is r is equal to something. All the other answers are matching exactly with this one only. So that's why option 1 has to be the answer. All right. From the Sakur-Tetrode formula for the entropy of a classical ideal gas, answer the following questions. What is the change in entropy per particle of an ideal gas that is subject to slow expansion from initial volume V to final volume 2V, keeping temperature and number of particles fixed? So Saku-Tetrode formula here, this question I'm not going to solve at all because this is a very straightforward question. There is a Saku-Tetrode formula. You take that formula, you go from V to 2V. Basically, you replace V by 2V, and you have to see what is the difference in both the cases. The entropy that you evaluate in the first case, the entropy you evaluate in the second case. What is the difference that you get? You basically have to subtract the new entropy from the old entropy. That's it, and you get the answer. So this I am not going to go into at all. You have to directly use the formula and nothing else. There is no concept involved here. So I'm not going to evaluate this. Okay. Now we come to these questions. We showed in class that the entropy function S of u comma n may be explicitly calculated using this very general formula. E raised to the power of S u comma n is some integrals, and there is this product function. Okay. If the particles are such that not more than one can occupy a given step, then Q is plus 1. If there is no restriction, then Q is minus 1. We know that these are the two boson and fermion cases. The meaning of epsilon j is if there is only one particle in the entire system, then if this particle is placed on the step labeled j, then its energy is epsilon j. We know the meaning of all the terms, so we don't need to get into this. Consider the special case epsilon j is equal to j, Q is equal to plus 1, and capital M is equal to 4. Q is equal to plus 1 means the fermionic case. Not more than one can occupy a given step. Find S U n equal to 2 explicitly from above given equation. Also find the same thing by enumerating all possible configurations and compare these two results. Which of the following entropies is non-zero? Okay. So firstly, let's do by enumerating all the possibilities. Okay, let me copy the question first so that we can solve it there. Okay. Epsilon j is j, Q is equal to plus 1, and capital M is equal to 4, which is 4 number of steps are there. Right. So for n equal to 2, we have to do this. So since Q is equal to plus 1, my expression is going to become this: e raised to power s u comma n is these integrals d theta by 2 pi integral d phi by 2 pi e raised to I theta u. where u is not exactly fixed yet. E raised to power I phi n. N is fixed though. N is going to be a very specific number. Um, and this product is going to contain four terms. J equal to 1, 2, 3, and 4 because M is 4. So we have four steps. So for that, and each step has two different kinds of occupancies. Either there will be no one on that step, or there will be one particle on the step. Either no particle or one particle. So enumerating all those possibilities will require four terms. 1 plus e raised to power minus I theta. Epsilon j is just j. E raised to power minus I theta j, where j is 1 first. I theta plus phi theta plus phi, and q is 1. So this is one term. The second term is 1 plus e raised to power minus I theta plus j is 2 now. So 2 theta plus phi. 1 plus e raised to power minus I 3 theta plus phi, and 1 plus e raised to power minus I 4 theta plus phi. Alright, so now what we are supposed to do is we have to multiply it out. We have to multiply out all the brackets and see what the answer we get here. What's the answer that we get? Um, so the first term is going to be 1. What I'm doing now is just evaluating these bracket terms. The integrals will evaluate later. So let me first evaluate the brackets. So the brackets are 1 plus, first term is e to the power minus I theta plus phi, plus 1 from everywhere. Actually, no, let me evaluate it like this. 1 plus e raised to power minus I 2 theta plus phi, 1 plus e raised to power minus I 2 theta plus phi, plus e raised to power minus I theta plus phi, plus e raised to power minus I 3 theta plus 2 phi. This bracket is going to be multiplied with the other bracket, which is there also I'm multiplying the last two terms, which is 1 plus e raised to power minus I 4 theta plus phi, plus e raised to power minus I 3 theta plus phi, plus e raised to power minus I 7 theta plus 2 phi. Now we expand entirely. So it has 1 plus e raised to power minus I 4 theta plus phi square minus I 3 theta plus phi, plus e raised to power minus I 7 theta plus 2 phi, plus e raised to power minus I 2 theta plus phi, plus e raised to power minus I 6 theta plus 2 phi, plus e raised to power minus I 5 theta plus 2 phi, plus e raised to power minus I 9 theta plus 2 phi. Actually, if you pay proper attention to this, what's happening in this one is we are basically multiplying possibilities. See these four brackets. I'm just telling you what's conceptually happening here. In these four brackets, first one is a possibility that there is no particle on step 0. Second one is the possibility that there is one particle at step 0. No, step 1, sorry. There is no particle at step 1, there is one particle at step 1. These are the possibilities. There are no other possibilities. There can't be more than one particle on step 1. The second bracket is also saying something similar. There is no particle on step 2, there is one particle on step 2. Why 2 theta here? Because the energy for being on step 2 is double. But the particle count which is given by phi is just 1. Similarly, the third bracket is telling me that there is either no particle on step 3 or there is one particle on step 3, which will give me 3 times the energy and just one particle contribution. Similarly, the fourth bracket tells me about the fourth step. So each bracket is telling me about individual steps. And what I'm going to do is I multiply all the possibilities. When I multiply out all the brackets, it tells me all kinds of possibilities of having the particles in different steps. All possible combinations are going to be given out. That there is either just one particle, that there is no particle at all in the entire system. Like, because you have maximum two particles, this also exists as a possibility that there is no particle. Actually, we are not taking that possibility, but this is just an entirely blank thing for now. This is taking into account all possibilities, and then when you evaluate the integral, it will put into account the constraints that the particle number has to be 2 itself. So any other particle number will be eliminated. You will see that in action, how these factors, this e raised to power I theta u and e raised to power I phi n, how these play the role of those constraints will become very clear. And this bracket below, this bracket which I'm evaluating currently, the four factors, that is giving me all kinds of possibilities um, with four steps, and each step either occupied or unoccupied. It is giving me all kinds of possibilities. And then the above factors, exponential factors, are actually putting in the constraints. So that's what's happening physically. It's, if you think about it, that's a very interesting way of counting manually. The thing that you do by counting manually, you are doing it by solving an equation. So it's a very interesting way in which it's been put forth. Okay, so we were evaluating this expression, right? Right. So 7 theta plus 2 phi is already there. This becomes 9 theta plus 3 phi. My bad. I have to be careful here. 7 theta plus 2 phi. Yes. Here the last term is 9 theta plus 3 phi plus e raised to power minus I theta plus phi. I'm still evaluating the bracket now. I 5 theta plus 2 phi e raised to power minus I 4 theta plus 2 phi e raised to power minus I 8 theta plus 3 phi plus e raised to power minus I 3 theta plus 2 phi e raised to power minus I 7 theta plus 3 phi e raised to power minus I 6 theta plus 3 phi e raised to power minus I 10 theta plus 4 phi. All the brackets have been evaluated here. I put down all the brackets. Now all these terms are basically in an integration wherein there is d theta e raised to power I theta u and d phi with e raised to power I phi n, which is 2. So e raised to power I 2 phi. So now you can very clearly see how the constraint is being put in. All the terms, all these individual terms which will have say 3 phi, 4 phi, 3 phi or 4 phi basically, these will be eliminated because when these terms go for integration with d phi, there is e raised to power I 2 phi minus 3 phi or 2 phi minus 4 phi. So when I evaluate this integral with d phi, I get 0. So these 3 phi and 4 phi are indicating 3 particles and 4 particle configurations, which we are saying that they are not allowed because the total number of particles are just 2. So that is why I said that this exponential term here, when I put n equal to 2, this exponential term puts in the constraint that the total number of particles has to be 2. But the potential energy has no constraint at all. So all those terms will actually give me 1. So what will happen is only these terms with 3 phi, this becomes 0, 4 phi becomes 0, 3 phi becomes 0, this 3 phi becomes 0, and this 3 phi becomes 0. Everything else will yield an answer. No, 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 sorry. Even 1 phi will become 0. Even this will become 0. Even this is 0, and this is 0, and this is 0. So all the remaining terms will yield an answer where particle number is 2 phi. So no, even this is gone. So term 1, 2, 3, 4, 5, and 6. It seems that there are 6 possibilities. And each and every term, by the way, each of these terms will yield the answer 1 because integral d theta with this exponential, when I do from 0 to 2 pi, it actually gives me just 1. So each of these will yield the answer 1. So 1 plus 1 plus 1 6 times gives me the answer 6. So it is telling me that there are 6 possible configurations with this arrangement. With 4 steps and number of particles as 2, I have 6 possible configurations. That's what this is telling me. And now, without using the equation, what is the answer that we come up to? Each and every staircase, basically, I have to choose any 2 staircase and put in 2 particles. So out of 4 staircase, I choose 2 and put in 2 particles. So 4c2, which is 6. So I got the same answer. Now you will actually be thinking that this was so much easier, 4c2, while we took such a hectic, we solved using such a hectic method. But what you see is that here the counting was very simple. So I simply used 4c2 and got the answer. But there are cases where the counting is very complicated. You have to take cases after cases. The number of staircase, the number of particles could be very large, or the case could be different and very complicated. In that case, counting won't be very easy. But this, you put it in a mathematical equation solver, like Mathematica or something, and this will definitely yield the result. So that is why this method is way more effective. The whole reason why this method is something that Sir taught, he took actually some time to teach this method, is simply because it actually automates the manual counting process. So S of un equal to 2, we did explicitly by solving the above equation also and by enumerating all possible configurations, and we got the same answer. By comparing, we got the same answer. Now they're also asking which of the following entropies is non-zero. Which of the following entropies is non-zero? That's a second part of the same question. Oh, wait, sorry. So S of u equal to 4 and E is equal to 2. Actually, we have already listed all these configurations, possibilities. We have opened up the entire factor. So here itself we can do the counting. If you understand the concept which I have told you, you can do the counting here itself rather than actually evaluating individually each and every term, each and every possibility. So I would prefer doing that itself because it's easier to explain. Okay, so this is basically the entire bracket that I evaluated previously. Here, now what they're asking is u is equal to 4 and n is equal to 2. N is equal to 2 and u is equal to 4. How many configurations are there? See, u is equal to 4 here and n is equal to 2 here. The coefficients corresponding to theta is u and coefficient corresponding to phi is n. So u is equal to 4, n is equal to 2, there is one configuration, and u is equal to 4, n is equal to 2, there is no other configuration. So basically e raised to power s u equal to 4, n equal to 2 is equal to 1. The counting possibility actually tells me the exponential of entropy, right? Then I take ln on both sides. Ln e raised to power s is equal to ln 1. So basically s u is equal to 4, n equal to 2 is equal to 0. So this is the entropy value is 0 for this thing because there is only one possibility that I get. U equal to 5, n is equal to 2. Let's do for that. U is equal to 5, n equal to 2, I can see here. So this is one case. U is equal to 5, n is equal to 2. There is one more case. And there are no other cases. So u equal to 5, n equal to 2. The exponential of that e raised to power s u is equal to 5, n is equal to 2 is equal to 2. So therefore s is equal to ln 2. So this is non-zero. This is non-zero. U equal to 6, n equal to 2. U is equal to 6, n equal to 2. This is 1. U equals 6, n equals to 3. Here u is 6, n equal to 3. So this is not okay. Not allowed. So even this has only one possibility. When you have only one possibility, the entropy is 0. So this entropy is 0. Guys, can you see my screen moving or my screen has frozen? Someone please unmute and tell me, is my screen frozen or you can see my screen moving? It is moving. Okay, so but because here it's frozen, so I thought that maybe it's frozen. You can see that I have boxed two of the options and I have tick marked one option, right? You can see all of that. All right, all right, all right. Okay, so the fourth option, u equal to 3 and equal to 2. U equals 3 and equal to 2 is one option. U equal to 3 but not n equal to 2. So this is not an option. 5. Sorry. U is equal to 3 and is equal to 2 is only one option. So even this is 0. So only option number 2 is non-zero entropy. I hope you understood this question. I hope you understood how that multiplication of factors is actually enabling you to count. How do you put in constraints of n and u? It's a very interesting uh, way of counting. So I hope you can appreciate the interesting part here. Okay, assuming that you've understood this, let's move on to the next one. Okay, I'll first show you question number 6. Actually, I'll not show question number 6. Question number 6 is pretty straightforward. So what the question is using the formula, the whole expression that we have seen, using this formula, this expression, evaluate e raised to the power of s u n equal to 5 for the case epsilon j is equal to j and q is equal to plus 1. Q is equal to plus 1 means fermionic case. Epsilon j is equal to j is the same case that we considered, and m is equal to 4. So basically we have 4 steps. 4 is the number of steps that we have. It's a fermionic case. So each step can have either 1 or 0 number of particles. Each step can have either 0 or 1 number of particle only, not more than that. But capital N is equal to 5, which means we have 5 particles and 4 steps. How do you accommodate 5 particles in 4 steps without each step having more than 1 particle? That's not possible, right? That's clearly not possible. So what you will find is, in this case, whatever you do here, this factor multiplication will give you many factors inside, but the maximum e raised to power minus I some value of j into theta plus some value of k into phi. Each term in this multiplication will be of this form. Each term will have this form, j theta plus k phi, and here outside there is some, basically many terms like this, plus dot 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 dot, lots of terms like this. There is e raised to power I theta u e raised to power I phi into 5 because n is equal to 5. Okay, this is the multiplication, and you have d theta d phi integral by from 0 to 2 pi, 0 to 2 pi. So here, because there is e raised to power 5 and inside you will never find any of these terms which will have e raised to power minus I into 5. The maximum value of k that you can have here is going to be 4. This is going to be the maximum value of k. K is always going to be less than or equal to 4. So you can't have k equal to 5. So this entire integral will always give you 0. All the terms inside, even if you evaluate, multiply everything, all the terms individually will give you 0. Which means that this has no possibility, right? E raised to power s u n equal to 5 is equal to 0. That's the answer. Here, this is the answer. All right, now let's go for this question. Uh, we want to consider the special case of bosons now. Let's do this. So this is the last question that we're doing, and then we're done. Okay, so question number 5 is uh, again we're considering the special case epsilon j is equal to j and q is equal to minus 1. Q is equal to minus 1 means bosons, and you have m is equal to 4, which means there are 4 steps on which you are arranging particles. Okay, um, there are 3 quantities that you have to evaluate. I am going to be evaluating only one. S u is equal to 6, n is equal to 2. That's the only quantity I'm going to evaluate. The other quantities you can just see and evaluate accordingly. Um, Also, we'll enumerate the possibilities and see whether those match or not. Okay. All right. So let's go ahead calculating this. E raised to power s u is equal to 6, n is equal to 2. This is equal to d theta 0 to 2 pi integral d phi 0 to 2 pi. The constraining part of the equation is e raised to power I theta is 6, u is 6. So sorry, e raised to power I 6 theta multiplied by e raised to power I 2 phi. These are the constraining uh, expressions. And inside, it will be a multiplication of these factors. 1 divided by 1 minus 4 steps and 2 particles, right? Alright, 1 minus e raised to power I theta j. Epsilon j is just j, which is 1 for the first term. I theta e raised to power minus I 1 divided by 1 minus e raised to power minus I theta is to power, sorry, 2 theta is to power minus I phi. 1 divided by 1 minus e raised to power minus I 3 theta raised to power minus I phi. And 1 by 1 minus e raised to power minus I 4 theta e raised to power minus I phi. These are the four terms which we multiply and evaluate. So again, as usual, I'll first evaluate only this part. One, 1 minus e raised to power minus I theta raised to power minus I phi minus I phi minus e raised to power minus I 2 I theta e raised to power minus I phi plus e raised to power minus 3 I theta raised to power minus 2 I phi. That's my first term multiplied by second term, which is 1 divided by 1 minus 3 I theta or minus I phi raised to power minus 4 I theta raised to power I phi plus e raised to power minus 7 I theta raised to power minus 2 I phi. Okay, Okay, I think actually a much better or easier approach would be, rather than actually multiplying out entire factors, what we can do is individually, we know that 1 upon 1 minus e raised to power minus I theta raised to power minus I phi is actually the sum of a GP, which will give me e raised to 1 plus e raised to power minus I theta raised to power minus I phi plus e raised to power minus 2 I theta e raised to power minus 2 I phi plus so on up till infinity, right? Here the common factor is e raised to power I theta minus I theta into e raised to power minus I phi. That's my factor by which my individual GP term is increasing. So let's use this to evaluate rather than actually going this way, because evaluating an integral with this huge term in the denominator is going to be very tough. So this is my first term. Let's go ahead and see what the second term is. 1 upon 1 minus e raised to power minus 2 I theta e raised to power minus I phi. I hope you understood how I wrote this one, how I wrote this entire series. So basically 1 plus r square plus dot 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 up till r raised to power n minus 1, basically till infinity. Actually the sum of this kind of a series is 1 upon 1 minus r, so where r is the ratio between the adjacent terms. So that's why, assuming that this is the ratio between adjacent terms and 1 is the first term where it starts, so that's how I've written this: 1 plus the ratio multiplied by the ratio square plus the ratio square plus the ratio cube, etc. So that's how I've written the GP. Similarly, for this second term, the GP will be 1 plus e raised to power minus 2 I theta e raised to power minus I phi plus e raised to power minus 4 I theta e raised to power minus 2 I phi plus so on and so forth. The third term will be 1 minus e raised to power minus 3 I theta e raised to power minus I phi is equal to 1 plus e raised to power minus 3 I theta e raised to power minus I phi plus e raised to power minus 6 I theta e raised to power minus 2 I phi plus dot dot dot. There are other terms which I am not writing down, and I will tell you the reason why I am not writing those down. 4 I theta e raised to power minus I phi is equal to 1 plus e raised to power minus 4 I theta e raised to power minus I phi plus e raised to power minus 8 I theta e raised to power minus 2 I phi and so on and so forth. Okay, now what I want to evaluate is u is equal to 6 and is equal to 2. What I have to do according to the calculation is multiply all these four terms and write down the entire expansion. So let me do that, but I'll not write all the terms, of course. I'm just writing down the bracket terms. 1 plus e raised to power minus 2 I theta I'll write down terms only, like the first three terms only I'm multiplying. Others I'll keep it as unknown terms. I will multiply only three terms. So 1 plus e raised to power minus 2 I theta is power minus I phi plus e raised to power minus 4 I theta e raised to power minus 2 I phi plus e raised to power minus 3 I theta e raised to power minus 2 I phi. Next, the term that I multiply will give me 3 I phi, which I don't want because my number of terms is just 2. Wait, let me see whether number of terms is more than 2 anywhere. No, I have to constrain the number of terms as 2. So phi I will constrain at maximum 2 only. I will not go beyond 2. So the next term, if I write down, is going to be 3 I phi. So I'm not writing that term. I'll write directly plus e raised to power minus 2 I theta e raised to power minus 2 I phi minus 2 I theta minus 2 I phi. The other terms will give me 3 or 4 I phi. So I am not writing them. Plus dot 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 multiplied by, again similarly for the last two terms, 1 plus e raised to power minus 4 I theta e raised to power minus I phi 2 I phi plus e raised to power minus 3 I theta e raised to power minus 2 I phi, sorry, just I phi minus I phi plus e raised to power minus 7 I theta e raised to power minus 2 I phi plus e raised to power minus 6 I theta e raised to power minus 2 I phi. There is one more term here, so I'll write that down also. Oh no, I've already written it. Sorry. Yes. So this is these are the terms that we have. Right, I have multiplied two brackets, and we have these terms. Now I will further multiply the two brackets. 1 plus e raised to power minus 2 I phi e raised to power minus I theta minus 2 I theta e raised to power minus I phi. Okay, let's, because my first term is 1, this entire term will be there as it is. If you are not able to follow the calculations, please do them yourself. Here, my job is to just outline the method, right? So this is the first term because I'm multiplying 1 with this entire bracket. So the entire bracket will come in right there. Next, this second term, e raised to power minus 2 I theta e raised to power minus I phi, I multiply with all the terms. So e raised to power minus 2 I theta e raised to power minus I phi plus e raised to power minus 6 I theta e raised to power minus 2 I phi plus e raised to power. The next term gives me 3 I phi, so I don't write that. Next gives me, yes, minus 5 phi I theta is to power minus 2 I phi. So I write this down. The next term gives me 3 I phi and 3 I phi, so I'm not writing them. And after that, all the terms will yield only one terms. E raised to power minus 4 I theta e raised to power minus 2 I phi plus e raised to power minus 3 I theta e raised to power minus 2 I phi plus e raised to power minus 2 I theta e raised to power minus 2 I phi. That's it. That's it. These are all the terms with 2 I phi, and there are many more terms, but we don't care about those terms. So what I've written down are the terms which you need to consider. Even amongst these, n equal to 2 eliminates all the other terms. N equal to 2 eliminates 1. It eliminates these kinds of terms which have just 1 minus I phi. Only these kinds of terms. In the exponential, there is only minus I phi, not minus 2 I phi. So these terms are also eliminated. Wherever there is just minus I5, even these terms are eliminated. What survives is only 2I5 when n is equal to 2. So now the question is, again, going back to the question, u is equal to 6, n equal to 2. What is the entropy in that case? U is equal to 6, n equal to 2. U equal to 6, n equal to 2. There are two possibilities that I can see here. So the entropy is ln 2 in that case. For the second case, u equal to 4, n equal to 2. U equal to 4 and n equal to 2. There is one case. Photo is already here. Three, 5. I think I'm not here. Okay, I missed a term here. There should have been e raised to power minus 3 I theta to power minus I5. Sorry, e raised to power minus I theta minus I5. Just this. To power minus I theta minus I5. And this when multiplied with e raised to power minus 3 I theta would have yielded one more. Is minus 4 I theta is to power minus I5. 2I5. This logically also it tells me that there should be two such terms. So basically I might have goofed up in the multiplication part, but if you evaluate this correctly, this is what you get. Even here there will be two such possibilities. So in this should be ln 2. U equal to 4 and equal to 2. So it can be step 1 and step 3, one particle each, or two particles at step 2. Yes, clearly. U equal to 7 and equal to 2. U equal to 7 and equal to 2 with 4 steps has one possibility here. Actually the final one, let's see. It has one possibility here and no other possibility. So this has to be 0. So yeah, so this is your answer. This is your final answer. And this is how you're supposed to evaluate these questions. Alright, so we are done with the entire assignment. If there are any doubts, you can post in the forum or you can ask right now. Does anyone have any doubts? Alright then, see you in the next session, guys. Bye bye.